Okay, we're taking a look at 22.40. There's a very long solid cylinder, so let's draw one of those. Here it is. Okay. It has radius capital R, and it's chock full of positive charges, so that it has a uniform, it has a charge per unit volume rho here. Okay. And they want to find the electric field inside of it. So we're going to be taking making a Gaussian surface that is on the inside. It's going to be on the inside of this surface, and it's going to have a radius of small r, maybe. There we go. Okay, so it's going to have a radius of small r, and we need to find out what that is. Okay, so in order to do that, we're going to set up Gauss's law, which I'm going to write. E dot dA equals quank the enclosed charge over epsilon naught. Okay. Again, we're going to have a uniform field across my Gaussian surface, which is another cylinder. So it's going to be E times 2 pi r L, the length of the cylinder. Again, we're hoping that divides out because that is not information we're given. So, and the enclosed charge is going to be rho times the volume of our little segment divided by epsilon naught. And again, the volume of a cylinder is just going to be what you'd expect. The area of the circle, pi r squared times L, the length of the cylinder. And again, we got E 2 pi r L. That's pi. Okay. All right. You can see the pi's are going to divide out, but the r that's tucked in there is not. The l's are going to divide out. That's convenient. Okay, that's sorry, I didn't finish that. Epsilon. So, okay, and that means E is going to be whatever's left, which is going to be rho. There is an r squared up here, and the r, that's what it does divide out. And we're going to have just rho r over 2 epsilon naught. That's going to be our electric field on the very inside of it. In part B, they actually want us to ignore that charge density, the volumetric charge density, and want us to look at it from the point of view of the charge density lambda. Well, hopefully you've done this problem a whole bunch. If you haven't, let's go over it again. Okay, we're going to start with Gauss's law. E dot dA equals quank or epsilon naught. Okay. And again, it's a Gaussian cylinder, and it's on the outside, so it's going to be E equals, or times, sorry, 2 pi r L equals, it's a charge per unit length, so it's going to be lambda times L, because that's going to be because that's going to give us the total charge divided by epsilon naught, and that's going to end up as E equals, because these divide out, lambda over 2 pi epsilon naught r. Okay, and hopefully you've seen that one a bunch before. Okay, and that's part B. Again, I'm not sure why they asked for it, but I mean, I guess they asked for it because they want you to compare those two answers for r equals r, and to remind you what our answer was for the other one. For part A, it was E equals rho r over 2 epsilon naught. Okay. Now wants to compare them for if r equals big R, the radius of the whole kit and caboodle, the radius of the entire cylinder. So let's plug it in, and that means that this becomes rho capital R over 2 pi epsilon naught. And this becomes lambda over 2 pi epsilon naught capital R. Okay. And let's define what these things are. Remember that the rho is a charge unit density. So it's going to be the total charge divided by the entire volume of the cylinder. So I'm going to replace rho. So rho is going to be charge per pi capital R squared L. Notice again, I use capital R because that's the entire cylinder. So now I can replace that. So I've got Q R over, I'm sorry, that's gone. Okay. 2 pi epsilon naught capital R squared L. And if I reduce that further, I get, because one of the R's divides out, I get Q over 2 pi epsilon naught RL. You can see that's looking an awful lot like what we had over in the other one. Okay. So for that one, they want the charge per length, which again is as easy as it looks. Lambda is just Q over L. So if I replace that, I'm going to get Q over 2 pi epsilon naught, that's terrible, pi epsilon naught RL. And you can see that this one, the one on the left, is equivalent to the one on the right. And we're going to get the same electric field for both of them at that point. So that works out great. 22.40D asks us to graph it. But that's kind of a tricky deal because it never did ask us to find out what that electric field magnitude is when we're outside that cylinder. So we have to quickly do that just to make sure we graph it right. So I'm going to do that up here on the top. So it's going to be, again, E dot dA equals quank, enclosed charge over epsilon naught. Okay. And that's still going to be E times 2 pi RL. And this is still going to be, this time it'll be a little different though, because it'll be rho times the entire volume, which is going to be pi capital R squared L. Remember, once we leave the outside of the cylinder, the enclosed charge won't get, we won't get more enclosed charge by being farther from the cylinder. The maximum amount we can get is at that distance capital R away from the cylinder. So it's going to be like that. And that's going to be epsilon naught. Again, the L's divide out, the pi's divide out. And we get a slightly different expression from last time. We get E equals rho R squared over 2 R epsilon naught. So this time it's going to actually be inverse. It's going to depend on 1 over R. Our variables, as our variable gets bigger, our electric field is going to get smaller because we're getting farther and farther from that cylinder. So now when I make my graph, here's E, and here is, we'll make markings at 0, R, they want 2R, and 3R. So in our first expression, it was rho R over 2 epsilon naught. So it's actually going to get bigger as we go. Sorry, it's going to be a straight line. Okay, until it gets to rho capital R over 2 epsilon naught. That's the biggest it's ever going to get. Then it's going to be a 1 over thing. So it's going to get to like 1/2 what it was, then 1/3 of what it was, and it's going to drop down from there. So that's what our graph should look like for the entire segment or entire part that they ask about in the problem.